Hello everyone, welcome to Vocabulary of Physics. And in this video, we are going to discuss about another important two words, symmetry and conservation laws. So let's get into the details of it. First, let's understand the disorder, which is a way of opposite to symmetry. So what is a disorder? First thing is it's going to be very messy, no pattern. You can't understand how the sequence is coming there. And it might appear there is no prediction at all. You cannot predict it, what is going to happen. Whenever there is a consistency, you can predict. When there is no consistency, you can't predict. It is like throwing a dice. So whatever number comes, we just have to take it that way. And there is no cause-effect relation. So you cannot link two events that happen simultaneously or one after the other. So if there is no cause-effect relation, you will not be able to conclude anything. If this is the world that we live in, then there cannot be any development for a human civilization. Luckily, we are not that kind. So let's get into the symmetry now. Symmetry, what is symmetry? To explain the definition of it, better to talk about in terms of the properties. What does it do? First of all, there will be a regularity of a kind. Some regularity has to be there and there should be a proportionation. So for example, in this diagram, you see with respect to that vertical symmetric line, there is a proportion, left half and right half, they are equal in size. And also there should be a repeatability. So there is some pattern that is getting repeated. So whenever you have these kind of properties, there will be some invariance. Invariance meaning something which is not going to change here. So invariance is an inherent property of symmetry. That is also one more thing. These are the properties that we have. So let's take examples of geometrical symmetry. That's the first thing that we can study about geometrical symmetry is reflection symmetry. So you see that water surface behaving like a mirror because of the reflection. So the lower half and upper half, they have a symmetry. You can see if you fold them about that line, they exactly match. So you can call this as folding symmetry as well, mirror symmetry or reflecting symmetry and so on. The next one is rotational symmetry. So if I rotate by some angle and keep it now as it is, you see that there would not be any difference between what you had originally and now. So even if you rotate by some angle, nothing is changing. We call it as rotational symmetry, or otherwise this word isotropy. The next one is translational symmetry. So imagine that you are on this particular brick and you look at the pattern. And from here you jump over to this brick and you will see that the same kind of pattern is repeated there. Next, we have point symmetry. So imagine that you are at the center initially and from there you travel in any direction. You will encounter the same kind of the path. That means there is a point symmetry with respect to the center. And then we have helical symmetry, example like you have double helix DNA shape. And so we have chiral symmetry. It is especially observed in chemistry, isomerism. So chiral symmetry is a kind of reflective symmetry and then rotation. That is what you have here. Then we go for symmetry in mathematics. Mathematics, there are a lot of symmetrical ideas there. I'll not go into the details, but I'll just give you some ideas just to understand, appreciate the symmetry ideas in mathematics. First one is palindromic symmetry. You have a reflective symmetry in a number. You look at with respect to the middle, you have left-right reflection symmetry or folding symmetry. And then we have this algebraic operations. There is a reflective symmetry. A plus B equal to B plus A. A into B equal to B into A. Of course, A minus B is not equal to B minus A. So it doesn't work out all the times. But whenever there is a symmetry of this kind, we call it as a cumulative symmetry, commutative symmetry. And then we have cyclical symmetry. So I cap cross J cap equal to K cap and J cap cross K cap equal to I cap, K cap cross I cap equal to J cap. This is in map. In vectors, you study this. So we call it as cyclical symmetry. I, J, K, J, K, I, K, I, J. That cyclical, you will see that. And then similarly, if you go for matrices there, you will see that with respect to this diagonal, there is a reflective symmetry. We call it as a transposal symmetry here. Then we have this algebraic numbers, algebraic expression that you have, identities. So you see the power of powers of A are decreasing, power 3, power 2, power 1 and so on. And powers of B are increasing. You look at the coefficients 1, 3, 3, 1, there is a reflective symmetry about that coefficients there. We call this as a kind of symmetry. And more generally, if you go for, it's a Pascal's triangle, which is used in binomial theorem to identify the coefficients of a binomial expression. So there also you got a symmetry there. Next, we'll look at finding the center of mass using symmetry. Take these symmetric diagrams like square, triangle, and cylinder you have here. So one method is to use integrations and so on, like integral r bar dm by integral dm is a calculation of center of mass. That don't worry about the relations there. But there is another conclusion. Whenever the mass distribution is uniform, the center of mass should coincide with geometric center. And it is a point where you can actually support it using a finger. If you just keep the finger at the center of mass, it will just support it, will not fall off. So that can be identified using the perpendicular, the diagonals, point of intersection of the diagonals will be the center of mass over here, which is the center of symmetry. And for the triangle, you just draw the medians, which divide the triangle into two parts. So three medians are concurrent at a distance h by 3 from the base and 2h by 3 from the vertex. You know it's center of mass. And similarly, for a cylinder, it will be on the axis, that's the axis of symmetry, and exactly the midpoint. So that way, we can directly calculate center of mass, which is a geometric center whenever mass is distributed. So that can simplify the problem. Similarly, let us take another example of finding a current using symmetry here. If you don't use symmetry, there is a method, Kirchhoff's law, junction law and loop law. So there are how many? You have 12 branches here. So you can imagine 12 currents and then write loop equations and try to solve them by creating as many variables that are required here. And so on, that's one method, very lengthy method. But if you use symmetry, definitely there is a symmetry. You see that with respect to this horizontal line, the up and low, there is a reflection symmetry. And same way with respect to this vertical line, there is a left-right symmetry as well. So by using the symmetry, you can say that current through this must be equal to current through this. Current through this must be equal to current through this. Current through this must be equal to current through this. Current through this must be equal to current through this. Current through this must be equal to current through this. So using that idea, these two can be connected together by splitting the junction. And these two can be connected together by splitting it. So once you split it, you see that the problem becomes very easy. Even a 10th grade student can solve it using the idea of parallel and series combination. So such a complicated looking diagram can be solved easily by using symmetry. So one example there. There are other types of symmetry. We call one temporal symmetry that's related to symmetry on time, future and past. Even if you reverse the time, if the things appear the same, we say it is temporal symmetry. Example, you take pendulum oscillating, you take a recording of it in a video. After that, if you rewind it, it would look the same. You cannot identify whether it is forward or reverse. So that is one kind of symmetry you have. Same way, another example, let's say you kick a ball in air. It goes in a parabolic path if you neglect the air resistance there. So what is the force acting? Gravitational force. By using kinematics, we can actually find the path of it. The motion can be described completely using mathematics. Now, if you run it backward, and if you try to use physics laws, if you are able to get the same thing, you would get the same thing. That means it has got a temporal symmetry. Whether you go forward or backward, physics laws are valid. That means these physics laws that we are using here are temporally symmetric. That's the basic idea you have. Then we have fundamental study of symmetry here. So there is a lot of study about the symmetry. So is the universe trying to say something about it in terms of the symmetry? That has been the curiosity of many scientists and mathematicians. They've studied a lot about symmetry and they found that the symmetry is related to some conserved quantity. There is one theorem, Noether's theorem, which says for every continuous symmetry in the action of a physical system, with the conservative forces, there exists a corresponding conserved quantity. So what it simply says is that whenever there is a symmetry, I'll not go into the technicalities of the words. Whenever there is a symmetry, there is a corresponding conserved quantity. That's what M.E. Noether's theorem says. So example, let us consider whenever you have a time symmetry, that would correspond to conservation of energy. Let's not go into the mathematics of it, but just understand the symmetry of this is leading to conservation of energy. Same way, spatial or translational symmetry corresponds to conservation of momentum, and rotational symmetry will lead us to conservation of angular momentum. So every symmetry in physics would lead to some conservation principles there. What is conservation law? The law which states that a certain quantity of an isolated system remains constant or conserved. This is called conservation law. It's like a cosmic currency. So there is one famous statement by Feynman, a great teacher, which says the beauty of nature lies in its simplicity. Just as the same key unlocks many doors, a single principle like conservation can explain many physical phenomena. So actually in physics, we use these conservation laws a lot, and they are very useful for us in solving a lot of problems and also dealing with many complexities here. So now what are the uses of symmetry? First one foremost, simplifying calculations is very important for us. And then finding conservation laws using conservation theories and all. Then we have predicting a new solution. Of course, there could be other way of solving a problem using symmetry. That's another thing. Guiding experiments. We can expect what to be tested using experiments. So that way it can help us guide certain experiments, and also it can strengthen the theories and refine them further for further understanding and scrutiny. So symmetry can also fuel great breakthroughs. Just to explain that, I'll take two examples. Let's read these statements carefully. When an unsteady magnetic field produces electric field, why can't an unsteady electric field produce a magnetic field? So even if you don't understand the statement completely, so what he's saying is, if this can produce this, why not the other way around? It's like he's looking at the symmetry. If this A can cause B, can B cause A? That is the idea. So using that idea, he went on to study about this electricity and magnetism. He proposed a new theory, displacement current, and also he combined electricity and magnetism together as one entity. And in the process, he proved that light is an electromagnetic wave by calculating C equal to 1 by root mu naught epsilon naught equal to the experimentally established value. So that is very important breakthrough for us in electromagnetism. And one more statement, you read it. When light exhibits particle nature, photon theory, light is a collection of photons, we say that. When light exhibits particle nature, why can't the particle exhibit wave nature? This is another question proposed by de Broglie. So he proposed matter waves, saying that matter also exhibits wave nature. De Broglie wavelength, very famous, which is the basis for quantum mechanics. That way, many breakthroughs also are driven by symmetry. So with that, I'll conclude here. These are the words that I've used in this particular video. So please go through these terms, try to understand them in the context of physics. With that, I'll conclude. Thank you very much for joining me. And until next time, goodbye.